Hey everyone, and welcome to the Basics of Information problem number 2. Before we begin, we'll just review a little bit of terminology. So variable length encodings use different numbers of bits to encode different symbols. So one example of that would be a Huffman encoding. And fixed length encodings use the same number of bits to encode every character or every symbol. So an example of fixed length encoding schemes, we have ASCII, and that comes with UTF-8 for 8 bits per character, or UTF-16 for 16 bits per character. And the bottom line is that we can shorten overall message lengths by exploiting the fact that there are different frequencies or probabilities that different symbols will occur, and for instance, E's are more common than Q's or something like that, so we'd want to devote fewer bits for an E. The first part of this problem, part A, is going to ask, Huffman and other coding schemes tend to devote more bits of information to, and then they give us some choices. So if we go ahead and think about it, we have more bits, more information. Means something hopefully would be more surprising, right? And less frequent. We want to devote more bits to things that don't happen as often. So that means that we can use more bits to represent the things that happen less often, because they'll add length less frequently to the message. So more bits, more information. So the answer is going to be more information for more bits. Symbols carrying the most information, right? Okay, now we have problem 2b. And in this problem, we are given 2 Huffman decoding trees for a variable length code involving 5 symbols, 2 possible trees, and we are asked to use tree 1 to decode this message. So the message, writing it out, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 1. So the first symbol, we have 0, and if we trace this down on the tree, we just get to A, right? So 0, stop, it's A. 1, 0, 0, stops at B. Now, 0, again, just stops at A, there's nowhere else to go. 1, 1, 1, stops at E. And then 1, 0, 1, stops at C. So now we have our message decoded. And moving on to problem 2c. In problem 2c, we're asked which of the 2 trees given would yield shortest encoded messages averaged over many messages. So in order to think about how long many messages might be, we can get a figure for the average number of bits per symbol that we're going to be needing to use. So in order to figure this out, we probably need to know how many bits are used for each symbol in the trees. So for A, B, C, D, and E, correspondingly, in tree 1, we're going to use 1, 3, 3, 3, and 3. Tree 2, it looks like 2, 2, 2, 3, and 3. So we know that using the sum of the probabilities times, the number of bits we have to use for each symbol is going to give us the expected value for, the average bits per symbol for each different tree. And we have 0.5 times 1, A, 1 bit. 0.125 times 3 bits for all of B, C, D, and E. So we'll just say times 4. Tree 2, again, A is 0.5 probability, but this one uses 2 bits. 0.125 probability and 2 bits for both B and C. 0.125 probability and using 3 bits for both D and E. So this one was for B and C, and that one was for D and E. So we just need to simplify these and do some math. So 0.5 plus 3 times 0.125 is 0.375, and then we have 4 of those. And that gives us 4 times 3 plus 0.3, 1.5 plus 0.05 is 2. Tree 2, we have 0.5 times 2 is 1, plus 2 times 2 plus 3 times 2 is 10 different times we have to count 0.125. It gives us 1.25 plus 1 is 2.25. So tree 1 yields the shorter average messages. So in problem 2D, we want to use the probabilities for A, B, C, D, and E to construct a Huffman tree using the greedy algorithm that if you aren't familiar with, you can pause now to read, but I'm not going to bore you. So we're going to write down our probabilities here. I'm going to write down our starting probabilities because we're going to write down our starting nodes. We have A is 0.5, B is 0.125, as is C, D 0.125 also, and then E 0.125 again. So we're going to start by taking two of the smallest. So we have a four-way tie, we can just pick two. So we pick D and E, and then we add the probabilities for getting to either one of those to make a new supernode, DE, which has a probability of 0.25. So there's a probability of 0.25 that you have a D or an E. So we draw those two, and then we arbitrarily assign a 0 or 1 to each branch of, leaving the supernode DE. We do the same thing, BC, because B and C were the next two smallest. BC, two little legs coming out of BC for B and C, arbitrarily assigning 0 and 1. Now BC and DE are the two smallest, with a combined probability of 0.5. So we'll connect BC and DE, arbitrarily assign a 1 or a 0. Now we have BCDE up here. And now the two smallest nodes are A and BCDE. And the probability of ABCDE, our new node, is 1. So that's how we know we're done. We attach A to BCDE, and then that's our supernode up there. And that's it.